Hello, this is Glenn Porter for part 2 of the Science of Light. Now, before we start, I'd just like to say if you haven't watched part 1 of this lecture, it's a good idea to stop now and listen to and study the first lecture, because in the first lecture we sort of unpack the description of light. We describe what light is, and we describe it in different ways of wavelengths, wave theory and particle theory. But it's very important that you understand those basic concepts before you go into this part of the lecture. So if you haven't watched part 1, stop now, listen to part 1 and then come back to this lecture. Now, the lecture 1, we studied the concepts of what lighting is and how we can describe this type of phenomena and this type of energy. We describe it in the electromagnetic spectrum and so forth. But what we're going to do in this lecture, in this part of the lecture, is look at how light behaves, or the behavioral characteristics of light. And within that scope, we're going to look at concepts like reflection, refraction, transmission, dispersion, the inverse square law, and polarization. Now, to start the lecture off, what we might do is just kind of unpack some of these concepts a little bit and look at reflection and refraction. So what you see on the screen is a ray diagram that defines a lot of the key elements to describing the concepts of reflection and refraction. First of all, you've got the left-hand side, which is just rays of light traveling in air. And that white section is a transparent material. It can either be glass or water. The line between the left side and the right side, or the white space and the grey space, is the interface between the two sources, air and glass. Now, the first ray, the incident ray on the left-hand, the bottom left-hand side, incident light is light that falls upon the subject, or onto the object. So incident light is the light falling onto the subject. And so that incident ray is a way of just showing that the direction of the light, which is just symbolized in an arrow, if you like, and it's heading towards that interface between the air and the glass. The reflected ray that we see on the top left-hand side is the light reflected off that glass surface. So as the incident ray hits the glass surface, there's a part of that light is actually reflected off, and that little arrow shows you the direction of that reflected ray. Now, you might also notice the dotted line in this diagram. The dotted line is what we call the normal. And the normal is a theoretical line. It's not a physical line, it's just a concept. And the normal actually sits perpendicular to the interface of the object. So that interface, or that space where the glass and the air meets, the normal is drawn at 90 degrees, or perpendicular, or right angles to that interface or that surface. You might notice on the left-hand side, we've got the little symbols I and R. So that I symbol is the angle of incidence. And the angle of incidence is that angle between the incident ray and the normal. Where above that, we have the little R, and that angle is the angle of reflectance, and it's between the reflected ray and the normal also. Now, on the right-hand side, in that white area, which is a transparent material, either glass or water, let's just say it's glass for argument's sake, we have another ray emerging. Because it's a transparent material, we have a certain amount of light energy that actually transmits through that medium, and that's called a refracted ray. And the angle between the refracted ray and the normal, in this case, is the angle of refraction. So the key elements to this diagram are the incident ray, the reflected ray, the refracted ray, and the normal. So let's have a look at what reflection and refraction actually is. Now, Isaac Newton actually is a UK scientist, and 17th century UK scientists who actually come up with quite a lot of concepts and ideas within science. And one of those is the 3 laws of reflection, which we still use today in modern physics. Some of these are, or two of these are actually very applicable to photography and our photographic practice. That's why I'm introducing them to you. So the three laws of reflection from Newton's theories are, firstly, the angle of incidence equals the angle of reflection. The second law of reflection is the angle of incidence, the angle of reflection, and the normal all lie on the same plane. Not so important to photography, that one. And the third one, with a plane mirror, the virtual image is the same distance behind the mirror as the real object is in front. So let's explain those in a little bit more detail. So the first law of reflection, the angle of incidence equals the angle of reflection. Now this is a really handy concept because when we're working in the studio, we're constantly trying to position the lights in a certain way to get a certain effect. And understanding this angle of incidence equals angle of reflectance is particularly important when we're photographing shiny objects or highly reflective objects. We're either trying to minimize the specular reflection in shiny objects, that's the reflection of the light, and it's a very bright highlight, or we're trying to totally saturate the object with a complete reflection of the light so that it provides a specular highlight to give texture. Now, when we're shooting shiny metal objects, for instance, we need that specular reflection across the whole surface so that we get texture of that that shininess of the metal. So when we're trying to position light sources, we're always battling with this concept with angle of incidence equals angle of reflection, because we're either trying to avoid the reflection or we're trying to enhance the reflection. Now, this concept, the angle of incidence equals angle of reflectance, is the easiest analogy that you can use really is just the billiard table. If you bounce a white ball onto the cush of a billiard table, the angle of the white ball is equal to the angle of the angle that it hits the cushion is equal to the angle it reflects off the cushion. Angle of incidence equals angle of reflection. Pretty straightforward. So the second law of reflection is that the reflected ray, the incident ray, and the normal all lie in the same plane. So they're not really points or arrows of light. They actually can be considered as planes, and those planes are all parallel, or they're in the same plane. Now, the third law of reflection is something that you may have come across in your photography if you ever photographed or try to photograph objects reflected in plane mirrors. Now, logic would say that the reflected image on a plane mirror is located on the mirror surface, so that if you were to focus on the object reflected in the mirror will be in focus too. That stands to reason within a logical form, in a logical sense. But unfortunately, it actually doesn't work that way at all. If you've ever tried this yourself, where you photograph something, a reflection in the mirror, when you focus on the object, what often happens is the frame around the mirror will become out of focus. And this sort of conflicts with your logic to say, well, if I focused on the image on the mirror, why isn't the edge of the mirror or the frame of the mirror sharp? And that's because of the third law of reflection. The virtual image, the image that you're seeing reflected on the plane of glass, is in a virtual space actually the same distance behind the mirror as the object is in front. So this diagram kind of illustrates that. So there we have that plane mirror in the middle. We have our viewpoint over to the left, and our object, that arrow in the bottom left-hand side. When we view the reflection on the mirror, the distance, the physical, the distance in a virtual sense is actually that same distance behind the mirror, the V distance that you see there. So when you need to get the reflected object sharp, it's quite easy to simply focus on that object and it's going to be sharp. But if you look at your distance on your lens, your distance scale, you will notice that it is actually further than the actual mirror itself, and that's because of that virtual image, the distance of that virtual image that you're actually focusing on. So why is the edge of the mirror out of focus? That's because it's a issue with depth of field. So if you want the frame of the mirror sharp as well as the image of the object sharp, you need to use a depth of field that covers both the distance from the subject in front of the mirror and the mirror itself. Now we can see this effect with this image shot by one of our photography students. So what you notice, what Jason's done here is he's actually focused on the mirror itself, or the frame of the mirror, and the object reflected in the mirror, the car behind the vehicle, is unsharp. That's because that distance, or the depth of field that's needed here, is quite extensive. It's the distance from the mirror to the actual car itself. So that depth of field is quite large and probably almost impossible in this shot. So the third law of reflection implies that the distance of the image is the same behind the mirror as the object is in front. Okay, so now let's look at the three laws of refraction. And these are less important in photography or photography practice than reflection, except the fact that we create images, or the image formation is all about refraction, the light coming into a common point to form an image. So it is a very important part of our photography, but our photography practice doesn't kind of rely on this a lot. But nevertheless, it is important to understand a couple of concepts. So let's look at the three laws of refraction. The first one is that when light enters a more dense transparent medium, it slows down and then bends towards the normal. So light travels at 300,000 kilometers a second in a vacuum. In air, it travels slightly slower than that because air is slightly more dense than a vacuum. But when the light then travels into a more dense medium like glass or water, the light bends or refracts. Now, when it goes from a less dense to a more dense medium, it bends towards the normal. So the refraction or the bending goes towards the normal. Now, we actually see this phenomenon as kids when we're playing with sticks in water. So we put a straight stick into a pond or a swimming pool, and this stick looks bent. That's the bending caused by refraction. We know it doesn't actually bend the stick, but it looks like that because of the concepts of light and refraction. The second law of refraction is the opposite to the first one. So when light travels from a more dense medium into a less dense medium, so going, say, from glass to air, it speeds up. And when it speeds up, it also refracts and bends, but it bends away from the normal when it's traveling through into a less dense medium. The third law of refraction is that when light enters a medium at right angles, or 90 degrees, the speed of light is altered. It slows down or speeds up depending upon what medium it's going into. When it's at 90 degrees, it actually doesn't bend. So let's just look at another diagram that kind of illustrates that a little bit more easily. So the ray that we see on the left-hand side coming down, traveling through air into glass on a slight angle, as it hits the more dense transparent medium, it bends or refracts and bends towards the normal. On the right-hand side, we have the light traveling at 90 degrees or perpendicular to the air and glass surface. So as it hits the glass, it actually does slow down, but it doesn't bend because it's at 90 degrees. So that's what the third law of refraction is referring to. Now, another concept that we use quite a lot in photography is the concept of transmission. And transmission is light that passes through a transparent material. One of the most common applications of transmission is either light traveling through softbox material to diffuse the light in a studio, or when we use optical filters on our camera lenses. So in this diagram, what I'm referring to in transmission, or using as an example, is a optical filter, a yellow filter. And transmission can change the characteristics of the light. by the material that's transmitting through. So in this example, we've got a yellow filter, we've got white incident light coming from the left-hand side. It travels through the yellow filter and results in a transmitted light. So what is the transmission in this instance? The transmitted light in this case is a yellow light because it's traveled through a yellow filter. When we place a yellow filter up over our eyes, everything turns yellow because we're actually now viewing the result of the transmitted light, which is yellow, so everything looks yellow. But let's just sort of define this and break this down a little bit more. So here we have our example that I just used in the previous slide. We have our white incident light traveling down through the yellow filter and the resultant transmitted light. Now, if you remember back from the first lecture, we talked about the concepts of subtractive and additive color synthesis. So these models are quite active in the way we produce images. Now, a yellow filter, if you remember additive systems, red, green, and blue, when you add those three components together, you produce white light. So it's an additive. So you're adding them together, produce white light. You're also using a third of the component. So a third of the spectrum in blue, a third of the spectrum in green, and a third of the spectrum in red. Combine those three together and you get white. But in transmission, what we're doing with the yellow filter is we're using a subtractive concept. So a yellow filter is part of the subtractive synthesis, which is the yellow, magenta, and cyan, or CMYK, but without the black, cyan, yellow, magenta. And if you remember, when we discussed the subtractive syntheses, we said that the subtractive method actually uses 2/3 of the specimen rather than 1/3. All it does is actually subtract 1/3 out of the white light. Now, this is kind of what's happening here in this diagram. So a yellow filter actually subtracts blue out of the white light. So it doesn't add anything, but it actually subtracts the blue. So what we get as a result is a yellow light. Now, it's not just a yellow light. There are three ways we can actually describe the transmitted light in this effect. We can describe it as yellow. That's the most obvious one. But we can describe it also as minus blue. So the resultant transmitted light is without blue. Or we can actually use another way of thinking and say, well, it's a combination of green and red, which is the 2/3 of the spectrum of the yellow subtractive synthesis model. So those three concepts of the transmitted light are all the same. It's either yellow, it's without blue, or it's a combination of green and red. So there are different ways of looking at the result of the transmitted light, and that's the concept I kind of want you to understand. In this case, it's a very simplistic subtractive model, but there are other more complicated issues like polarization, for instance, that we're going to talk about later in this lecture. Now, a couple of values that you need to kind of know. It's probably not really important, but these are the way we measure these phenomena of light. There are 4 different values or measurements that we can use. Transmittance, which is measuring the light that's being transmitted through an object, like we just explained. And the formula for that is light transmitted divided by light incident. Now you can't flip it around the other way. You can't have light incident over light transmitted because you can't actually create more light by transmitting light through an object. It's got to be less light. There's got to be some loss of light or some scattering and some effect. So you can never actually increase the light because that's just not possible. So transmittance is light transmitted over light incident. Reflectance is exactly the same as transmitted, except it's not being transmitted through something, it's been reflected off. But the formula is the same, light reflected divided by light incident. Now, opacity might be a term that you're familiar with Photoshop. and it's used in a slightly different way with Photoshop. But opacity is kind of the amount of whether the object is see-through or not. So when we're using it in Photoshop, when we're dealing with layers, we can change the opacity of the layer on top so that we can see through it and see what's happening on the layer beneath it. So opacity is something we use in Photoshop, but in optical concepts, it's actually that amount of it's the reciprocal of transmission, or it's the reciprocal of reflectance. So it's 1 over transmittance or 1 over reflectance. Now, opacity is something we don't kind of really use in photography, but it serves this purpose, and that is to calculate the density. And density is used quite a lot in photography, and the density value is the log of opacity. Now, to give you an example where you might see this in photography, if you've ever used neutral density filters, which are filters that are used particularly in long exposure photography, where you want to increase the shutter time to get that effect of movement, or you're photographing a waterfall and you want a very soft, fluffy type of water and you want to use a long exposure, there might be a lot of light there, so you actually use neutral density filters to enable that long exposure. Neutral density filters are neutral in color. They just add density to in front of the lens and attenuate the light. But if you went to buy a neutral density filter, the sales person might ask you, well, what stopping power or what density would you like the neutral density filter? And you say, oh, well, what options are there? And they're usually 3 options, but sometimes 4. And you have a neutral density filter in a 0.3, a 0.6, a 0.9, and sometimes a 1.2, which is not pretty rare, but you can get them. So then you look back at the salesperson and go, well, what does all that mean? Well, you just have to stop and think about it. Neutral density filters are described in the density value, and density is the log of opacity. So a 0.3 density is what? Well, it has a certain level of density that stops the light. But how many stops does it actually stop? Well, the log of 0.3 is 2. If you look it up on your calculator, and in my day when I went to high school, we had tables. We didn't have calculators to do that, but that's another story. But if you look up the log value of 0.3, you'll notice that it's 2. Now, what does 2 represent in exposure? 2 times equals 1 stop. So a neutral density filter that has 0.3 density actually relates to a 1 stop difference in exposure. Does that make sense? So a 0.6 neutral density filter, if you look up the logarithmic value of 0.6, you'll find that that's 4, which is 2 stops. And 0.9, the log value is 8, which is 3 stops. And 1.2 is 16, which is 4 stops. So there's an example of how we use density within the concepts of photography. It's a very simplistic one, but one nevertheless. So neutral density filters are actually described in this density value. Now the transmittance and the reflectance, you'll also see those values in our spectral distribution curves, our filter transmission curves that we'll see, and we'll examine them in the infrared lecture as well. When we're trying to look at the characteristics of certain infrared filters, we describe them in its transmission or transmittance, which is the light transmitted over the light incidence. So we'll leave that for now. But these 4 concepts, transmittance, reflectance, opacity, and density, not so much opacity, but because opacity is really just a way of getting to density. But those 3, transmittance, reflectance, and density, are used quite regularly in the scientific concept of photography. Now, in the first lecture, when we looked at wavelengths, and we discussed the concepts of the difference between red wavelength at, say, 700 nanometers and blue wavelength at 400 nanometers, and we suggested that 400 nanometers has a higher frequency. Both of these light source or wavelengths traveling at 300,000 kilometers a second in a vacuum, but they have either more peaks or less peaks across the same distance. And we suggested that can be related to two things. It can be related to the concept of frequency. So the amount of peaks over a certain distance so blue has more frequency or more peaks, so it's higher frequency than red. Red has less amount of frequency of peaks across the same distance. And the other thing that we kind of discussed was that you can look at blue as being more energetic because it's moving up and down a lot more per distance. So it's more active or more energetic, more excited as a light source than red. Red's much more, it's a longer wavelength and it's much more lethargic, less energetic. Now this is important to understand the concept of dispersion. Now dispersion is simply the separation of the colors of white light when white light enters a prism or a more dense medium. So we've seen this in rainbows and we see this all the time in nature. But when we shine a collimated light source through a glass prism, a white light source, we start to see the separation of the colors, and that's what we call dispersion. Now what's happening here is that the red wavelengths being less energetic, when they hit the more dense transparent medium, they slow down because of the refraction, but because they're less energetic, they bend less. So when the blue wave separates because it has a higher frequency, the degree of bending or refraction is actually greater. So there's a disparity between the amount of refraction that occurs across the different wavelengths within the context of white light. And because they're different bending powers or refraction, we then get a separation of light, and that effect's called dispersion. Now dispersion is a real issue in photography because we have light traveling through these more dense mediums all the time, glass elements in our lenses. And lens designers have to control dispersion, and they have to, because when we're trying to bring our light to a point to form an image, with dispersion you've got several points. You've got red, green and blue coming to a different point because of dispersion. And this is a problem called chromatic aberration. And chromatic aberration needs to be corrected by the lens designers, and that's always been a problem. They can correct it pretty well these days through using different lens combination and elements to actually not just only bend and produce an image, but also to correct for this dispersion effect or correct for chromatic aberration. But just to sort of summarize dispersion is the separation of the colors of white light when it travels through a more dense medium like a glass prism and caused by the different frequencies of wavelengths. Now the next topic is inverse square law. An inverse square law is an effect that changes our exposure due to the distance of light. So when we've got a point light source, and if you look at this diagram on the right hand side there, we have our little bulb and we have a distance, a D1 or a distance 1. Now let's, for argument's sake, that is 1 meter. So if we have a distance of 1 meter, our area of coverage is 1 meter by 1 meter, which is 1 meter square. Now if we double that distance to 2 meters, so D2 equals now 2 or 2 meters, our surface area from the same light is 2 meters by 2 meters, which is 4 meters square. So 4 times the area. Now it's the same amount of energy because that light has X amount of energy. But the brightness on a 1 meter by 1 meter square or a 1 meter square area is significantly brighter than the same level of energy across a 4 meter square area. So inverse square law is suggesting that when you double the distance, you actually lose 4 times less exposure, and 4 times is 2 stops. Now, to put this into practical terms, if you're shooting, particularly in weddings or social functions or public relations photography, where you've got a person standing, say, 2 meters away, you're using your electronic flash because it's inside, and you have another group of people another 2 meters behind that person. So you've got 2 different distances here now. You've got your main center of interest, which is the person 2 meters away from the camera, and the group of people which are 4 meters away from the camera or away from the flash that's on the camera. Now, if you get the exposure right for your foreground subject, you will notice the group behind that subject is significantly darker because we've actually lost 2 stops of light on those people. So inverse square law is about this concept of distance of point light sources. So inverse square law is one of these laws that you really do need to become familiar with once you start lighting objects through electronic flash or in the studio. For basic photography, when you're using available light, it's not much of an issue. But it's as soon as you use artificial lights, inverse square law becomes quite an important consideration. Okay, now the last topic for this lecture is polarization. And polarization is a very complex concept, but I'll do my best to try to simplify it for you and to put it into some practical and applied ways for you so that you can use it in your photography. Now, first of all, let's just look at these 3 concepts and I'll unpack them with some diagrams. So unpolarized light oscillates in all directions as it traverses in the direction of the wave. It's very wordy, but I'll show you in a diagram. Polarized light, on the other hand, produces a single plane of light as it traverses in the direction of the wave. So we have multiple oscillations or single plane of light. The plane of light is called the plane of polarization. So let's have a look at a couple of diagrams so we can make sense of that. Okay, now let's look at the 2 top diagrams. First of all, the unpolarized light. Now, if we look at the diagram on the top right-hand side particularly, so as we know through the first lecture that light travels in a waveform. We're happy with that. We understand that. Now, if you remember in our first lecture, we had a wave diagram where we had the direction of the wave, the wave axis, which is that arrow going from the right-hand side to the left, and then we have the direction of the vibration, which is that line, that vertical line on that axis point. Now, what you'll notice in this diagram is that there are 2 wave formats. There's a vertical wave format going up and down, and then there's a horizontal wave that's going across the axes. But the 2 waves are actually traveling in the same direction and they're traveling on the same axis, but they have a different oscillation effect. Now, in unpolarized light, this is simplifying it. You've only got 2 waves. In actual fact, you've got hundreds of waves oscillating around that axis, traveling in the same direction. Now, the diagram on the top left-hand side that's what that's showing. So that little dark area in the center is the light axis, and if you like, it's coming towards you, towards the screen. So the direction of the light's coming towards you, and that center part is the axis. Those lines are all representing the planes of light that are oscillating around that axis. As you can see, there's quite a few. So unpolarized light is light that's traveling on the same axis, but all these different wavelengths are traveling on the same axis and at the same direction. Now, polarized light is represented in the 2 diagrams on the bottom of the screen. If we look at the right-hand side one now, we can see that the horizontal plane has been taken away and we've got one single wave. And that one single wave is one plane. And as you can see on the bottom left-hand little diagram, we have our axes there in the center. Again, this is coming at you now, looking straight on the axes, and we have one direction or vibration of that wavelength, and that's polarized light. So polarized light eliminates, or to get polarized light, you eliminate all the other oscillations around, or wave oscillations around the axes, so you've only got one left, and that one wave is a plane of polarization. Okay, so let's look at this in the same concept in another diagram. Now we've got three diagrams. So the one on the left, the unpolarized, you can see that axes and all the different waves traveling on different axes around that, on different planes on that axis. And we can see that again at the end of that diagram, we can see that it's oscillating in all those directions around the axes. The linear polarized, now we've got two concepts of polarization here now. We've got linear polarization and circular polarization. Now, linear polarization is that single plane, that single wave traveling in a straight line, traveling along the axes, the light axes. That single plane is a linear polarized. It's linear meaning straight up and down, or straight, linear meaning straight, and it's polarized because it's a single linear polarized light. Now, to add a bit more complication or a bit more confusion, we've got now a different type of polarization, and that's circular polarization. Now, I'll show you how circular polarization works in a moment, but try to imagine this. So we've got now the circular polarization is a polarized light, so it's a single plane of light. But instead of just traveling in a straight line in a linear fashion, it's actually spiraling. So that plane, if you can imagine, you get a piece of A4 paper and you then start to spiral it around. We've got this plane that's now acting and moving in a spiral way. So it's still a polarized light because it's a plane, and it still has a planar polarization. But instead of being linear, it is now spiraling and behaving in a circular way rather than a linear way. So let's kind of unpack that a little bit more. So what I'll do, I'll explain a little bit more how circular polarization works in a moment. And actually, circular polarization is a really critical thing because in modern digital SLR cameras, if you go to buy a polarizing filter for your camera, you have to buy a circular polarizing filter, not a linear polarization filter. And I'll explain why that is so in a moment. Okay, so let's look at some of the application of polarization. When you use polarized light, you are able to reduce the specular reflections. So little tiny white highlights of subjects can be not so much eliminated but minimized with polarized light. The interesting thing is that when you remove that level of specularity or the specular reflection off surfaces, you'll find that the color saturation increases. Now, this is a real key tip. If you're really into color photography and you like very rich color, particularly in your landscape work, polarizing filters are an absolute must. If you're photographing, say, in the rainforest and there's lots of green foliage and it's beautiful color greens, and you really want that rich green to sort of vibrate through your image, a polarizing filter, and you'll be surprised at the effect of this, and you certainly should try it. It will eliminate those specular reflections a lot of specular reflections off the surface of the foliage, and that will increase tremendously the green saturation you're getting from the actual plant material. So polarization, or through polarizing filters, we're able to use or achieve a much higher color saturation. Now this is a very different color saturation to what you can do in Photoshop and Adobe Camera Raw. It's not just bumping up the saturation. Polarized light is a natural way, and you cannot simulate the saturation that you get off a polarized filter on Photoshop. You can't eliminate those specular, the level of speculars on the actual objects. You can only do it optically through using polarizing filters and polarized light. So the concept of increased color saturation is very different than just increasing the color saturation on Photoshop. Very, very different concept altogether. Another advantage of using polarization is that you increase the transparency in water. Now, this is exactly the same point as the first point, really. By minimizing the reflection off the surface of the water, you get to see through the water a lot more. And living in far north Queensland, in a tropical environment where you want that beautiful aqua, crystal clear water, if you want that to be enhanced in your photography, a polarizing filter will just take that specular reflection again off the surface of the water, and the water will look far more transparent or far more crystal clear. So polarizing filters does that. But this is exactly the same effect as the green foliage. It's taking the speculars off the green foliage, whereas it's taking the specular off the water surface. So it's kind of the same concept, but the same result. So visually you get much more color saturation, much more or greater level of transparency through transparent material. Polarization helps to also darken skies. And if you darken skies, you increase that definition of clouds. So you've probably seen images of beautiful, rich blue, this royal blue kind of clouds and fluffy white, royal blue sky and fluffy white clouds. That's caused by polarized filters or polarization. Now, if you shot some landscape work without a polarizing filter, you might notice that in the blue skies that you get certain areas of the sky that's actually darker than others. It might either be on the horizon or higher in the sky, but you definitely see a different level of blue in the sky when they're shot in the daylight. That's actually an effect caused by polarization, because we do actually have natural polarization. At 90 degrees to the sun, the sky is naturally polarized. So that 90-degree angle from the sun, you'll find that the sky is actually a lot richer in blue because it's actually polarized light. Now, another polarizing technique that we use in photography is cross-polarization. And cross-polarization is when we use a linear polarizing filter on the lens and a linear polarizing filter on the light source. And we rotate the axes of the polarization at different orientations, and we get a cross-polarization effect. Now, cross-polarization effect is an application that we use to control specular highlights on very difficult subjects, like when we're photographing oil paintings, when we're copying oil paintings. The highly reflective surface of an oil painting and the uneven surface makes it very difficult to light. So to minimize those specular reflections, we use cross-polarization technique. But we can use also cross-polarization to get a birefringence effect. And the image that you see is one of my images that I shot some years ago of a CD cover using cross-polarization lighting. So this birefringence, or what we call double refraction effect, is the separation of colors. You get this beautiful kind of rainbow effect on these plastic materials. So cross-polarization is a technique that we can show birefringence. Now, in engineering photography, we can find that one of the techniques of building bridges and things is to build it out of this plastic material as a model and then put certain loads and stresses, and you can actually see where the loads and stresses are on structural material through this technique as well. So cross-polarization is a way of controlling difficult subjects with specular reflections, but also we can use it for this concept of birefringence. Okay, so there's some of the advantages of and applications of polarization. Let's look at how we actually achieve it. So first of all, we can achieve it naturally through the skylight. As I mentioned before, at 90 degrees from the sun, the skylight is naturally polarized. There's a natural polarization effect too that happens on all surfaces, or sort of reflective and transmitted surfaces. And this is called Brewster's angle. Now it depends on the refractive index of the material, but there are different angles for different surfaces. So if you're photographing, say, the chimpanzees at the zoo, at Taronga Zoo, say, and you're shooting through the glass, if you get on a particular angle of the glass, you can actually eliminate the reflection off the glass through polarization, and that reflection's minimized or taken away through a particular single angle, and that's called Brewster's angle. So Brewster's angle is another natural polarization phenomenon. The most common way that we use polarization is using polarizing filters, and there are two types of polarizing filters: linear polarizing filters, which are material that are long chain parallel molecules. So they're parallel long chain molecules, and they sit in long chains next to each other, a bit like a picket fence. And I'll show you how this works in a moment. Circular polarizing filters, as we saw in an earlier slide, it produces a spiraling plane of polarization, not just a linear one. And we'll look at a circular polarizing filter as well in a moment. Cross polarization, I've spoken about that, where we put polarizing filter on the lens and camera. Sorry, on the camera and the lights. And also we can depolarize light. So if we get polarized light, or polarized light can be depolarized when it's scattered or reflected off a diffuse surface. So either transmitted through a material or reflected off a diffuse surface, that will depolarize polarized light. So these diagrams kind of illustrate some of those concepts, some of those methods. So on the left-hand side, on the top one, we have Brewster's angle. So in this case, it's a glass surface, and at 57 degrees, the angle of incidence at 57 degrees, we get polarized light. As I say, it depends on the refractive index of the material, but it doesn't vary much around 57 degrees. So there's slight variations there, but it's roughly about the same angle. The second method, B, under that one, is natural skylight polarization, 90-degree angle from the sun. And if we look at across the right-hand side, we'll see two different locations of the sun. So when the sun's directly overhead, the horizon around the photographer is actually polarized light. When the sun is late in the sky, or at sunrise or sunset, just before sunset and sunrise, the polarized area is directly above the subject or the person, photographer. So it depends on the angle of the sun, but it's 90-degree angle of the sun, the skylight is naturally polarized. And the third method that we've got here on the left hand side is through a polarizing filter. And as you can see here, we've got our two wavelengths vibrating at different directions, traveling in the same direction but vibrating in different directions. And we have a polarizing filter, which is made up of these long chain molecules that only let light in through one vibration. So we can see that it eliminates one wave but allows a single wave to travel through, which creates polarized light. So just a couple of points on polarizing filters. It converts unpolarized light into polarized light. That's its function. There are two types, linear and circular polarizing filters. The circular polarizing filters must be used with modern cameras with autofocus, and certainly when you have the modern TTLs, or through the lens metering systems, need circular polarizing filters, and I'll explain why that is in a moment. Polarizing filters are neutral in color. They don't have any color bias. They're very neutral in color, but they do have a density, and that density is equivalent to about 1.5 to 2 stops. So you lose 1.5 or 2 stops exposure through the density of the actual polarizing filter. Don't forget the way it works, it actually is cutting out some of that light. So hence there is some loss of exposure. But it's neutral in color, which is important as well. You can use polarizing filters as neutral density filters as well, but the maximum you'll get is between 0.3 and 0.6 of a density, which is between 1 and 2 stops. So this is how linear polarizing filters work, and it's a very crude way of explaining it, but this is about the only way you can explain it, because polarizing is a very complex concept. So on the left-hand side, we have our unpolarized light, which is oscillating in all different directions from the light axis. In the middle, we have our linear polarizing filter, which is made up of these long chain parallel molecules, and it will only allow the wavelength at the same orientation to travel through the polarizing filter. And by doing that, we then get one single vibration or oscillation of light through the axis, which is a polarized light source or a polarized light. Now, the analogies that are often used when we're trying to explain polarization and polarizing filters is the picket fence. So if you had a picket fence and you had a stick, to try to get the picket fence through the stick, you have to orientate the stick on an axis so that it's a vertical, so it will actually allow the stick to pass through in between the two pickets. If you had the stick horizontally and try to get it through the gap of the picket fence, it's not going to get through. It's this sort of analogy, this sort of concept that's happening with the polarizing filter. So it's only that oscillating vibration that's at the same direction as the polarizing filter that actually gets through. Now, polarizing filters, if you've ever used one or going to use one, you'll notice that you screw them on the front of your lens element, but then you're able to actually rotate that filter around the lens element. So if you can think of the picket fence, so you've got these the gaps in between the long chain molecules, but you can have them horizontal, you can have them vertical, you can have them at any kind of direction. And this is important. So when you if you want to darken the sky, for instance, or you want to get water more clear, you not only put the polarizing filter over your lens, but you then rotate that filter until there's maximum amount of reflection being reduced. So that's very important with polarizing light, with polarizing filters, that you get the orientation. You can't see it. You can't actually see the gaps. They're invisible. They are there, but you can't see them with human eyes. But when you're looking through the camera, you will see quite a change happening when you rotate the polarizing filter. All right, so let's look at now circular polarization. Now, as we talked about before, circular polarized light is still a single plane of light because it's polarized, but that plane of light is actually spiraling as it's moving. You got to remember, light travels. It's not a static thing. So it does travel. So it's that plane in a spiral motion or circular motion. Now, circular polarizing filters are actually a combination of two elements. There are two elements sort of glued together in circular polarizing filters. The first one is your regular linear polarization filter. So it's the long chain molecules that act as a picket fence, and it only allows one vibration of light to go through to create a polarized light. Now we can see that in this diagram. We have our unpolarized light coming in from the right hand side, going through that linear polarizing filter at a certain orientation. It only allows that one vibration to come through, and now we have a linearly polarized light, a plane of polarization. The second element to the filter is a quarter wave retardation plate. Now, what the quarter wave retardation plate is that it rotates that plane by a quarter of a wavelength. So if it's 400 nanometers, it will rotate it by 100 nanometers. That's not really necessary to understand that, but what happens if you think of something that's traveling, a plane of something traveling, and then you just knock the top of it so it just tilts it over a little bit. So what happens with something that's traveling when you just make that adjustment? What happens is that it starts to spiral. So the quarter wave retardation plate then makes that plane of polarized light traveling in a straight line, it then spins it into a spiral, into a circular motion. So circular polarization filters are a linear polarizing filter to first produce a polarized light, but then it travels through this quarter wave retardation plate, which then sends it into a spiral, and that's what circular polarizing filters do. So most of your modern cameras need a circular polarizing filters. If you're going to use your autofocus or your exposure controls, your through the lens camera, your through the lens metering systems, you need to use a circular polarizing filter. And this is why, because most of the modern cameras these days use the mirror as a way of controlling the optical system or the metering system and viewing system in the camera. So if you look at the top diagram A, there we have a non-polarized light, and the light then hits the beam splitter there, our mirror in our digital SLR, and 75%. Now this ratio can change depending upon what camera manufacturer, but it's roughly the same for most of them. It might vary slightly, but it's a way of illustrating this concept. So the unpolarized light hits the mirror, and 75% of that unpolarized light goes to the viewfinder. So when you're looking through the camera, you see the image that you're focusing on. The other 25% passes through the mirror or through onto your sensors for your exposure meter. Now the 75 to 25% ratio is important because your light meter is calculating the exposure only based on 25%, because we want most of the light to go through the viewfinder so that the viewfinder is quite bright and we can see the images and focus properly and so forth. But it's quite easy for the computer inside the camera to recalculate that. If it knows it's only 25%, well, it measures the light, then increases it by 4, and then we get our correct exposure. But what's important is that ratio is consistent and stays the same. If we look at the diagram in B, we now use a linear polarization filter on one particular axis. This is on a vertical axis. So we start with non-polarized light. It goes through the linear polarization filter, which is, you can see there at L, and it's saying that it's on a 45-degree angle, and we get a polarized plane of light. Now when that polarized plane of light hits the beam splitter, in this case we're getting 62% going to the viewfinder and 38% going to the sensor for your exposure. So now we have a different ratio to the top. We don't have 75-25, we have 62-38. On the third example, so we have in C, we have non-polarized light going through a linear polarizing filter, this time on a 135-degree angle, so we get the plane of polarization horizontal, if you like. That's why it's represented in that circle. When it hits the beam splitter, our ratio now goes to 88 to the viewfinder and 12 to the exposure sensor. They've a different ratio altogether. Now when you rotate the polarizing filter at a different angle, you're going to get another different result. So the computers, the calculator or the computer in the or the calibration of the light meter depends upon getting the same amount of light. It doesn't know how much light it's getting in that variation caused by the polarizing filter. It must be constant. So you've got to keep that 75 to 25% split constant, so your exposure meter is actually going to work. Now the interesting thing with a circular polarizing filter, remember circular polarizing filters or the circular polarizing light works in a spiral effect. It doesn't actually have any orientation. Now, if we look at the bottom diagram, diagram D, we have an unpolarized light, and now we have our linear polarization filter with our quarter wave plate sandwiched together to produce a circular polarized light. Now, when that circular polarized light hits the beam splitter, we have our 75 and 25% ratio, the same as unpolarized light. So our calibration of our light meter remains intact, doesn't have to change. The funny thing is, because we're working in a spiral, if we change the orientation of the polarizing filter, because we can rotate it, it doesn't change the spiral. The spiral is still in the same direction. So that ratio of 75-25 remains the same. So circular polarizing filters are essential for modern cameras so that our exposure meters remain calibrated to the system that the camera's manufacturer has actually built into it. Linear polarization filters, you'll get inaccurate exposure. Also, the way the autofocus works, it interferes with the autofocus as well. So that's another issue that we have with just linear polarized light. You can still use the single linear polarizing filters if you want to focus manually and if you want to calculate the exposure manually. If you've got a light meter or you've got other systems, you can use it. So you can use linear polarizing filters on modern cameras, but you just can't use the autofocus or the auto exposure system. So if you're going to go and buy yourself a polarizing filter for your modern digital SLR, it's a good idea to get a circular polarizing filter, not a linear polarizing filter. Now, I mentioned before that the color of polarizing filters is quite neutral, and I tested this with a spectrophotometer on one of my BMW circular polarizing filters, and you can see they're very neutral in the color. So here we have actually our transmission in a percentage form this time. Remember, we talked about those 4 values of measurement. So I'm measuring the transmission values, but also measuring the color values as well. So, but as you see, from 400 to 700 nanometers right across that visual spectrum, it's pretty much flatline right across. That little bump on 650 is a artifact in my spectrophotometer. It's actually, and I need to add that to a correction, it's not actually the filter itself, it's an artifact in my spectrophotometer. So let's just summarize all the elements that we've talked about in the 2 lectures, part 1 and part 2 of the Science of Light. Initially, we talked about the difference between lighting and illumination. One is a concept of quantity. The other one is a concept of quality or aesthetics. We talked about how we describe light in wavelengths. We talked also about what light is in the concept of energy and how it's positioned within the overall electromagnetic spectrum. We looked at other concepts of considering light, the spectral distribution, so the distribution of the different colors within the white light. We talked about spectral sensitivity of cameras and what colors of the light or what radiation the actual the digital sensors and film is sensitive to. So spectral sensitivity is a way of describing what wavelengths we can actually record. We talked about the concepts of additive and subtractive color synthesis, additive being the RGB and using 1/3 of the spectrum in each of those values, and subtractive, which is CMYK, but the K is the black, which is the CMY, so cyan, magenta, and yellow. And that is 2/3 of the spectrum each and subtracts the elements out of the white light. So one's additive, one's subtractive. One's added together to produce white light. The other one subtracts away from white light to produce, well, nothing in the end. We looked at Maxwell's triangle, which is the relationship between the subtractive and additive synthesis and looking at opposites and opposing colors. We talked about color temperature, the way to be able to describe and measure the color bias of light sources. And of course, we use this in a practical term in our digital cameras with white balance. But white balance is what we're treating or setting the camera on to deal with the color temperature of different light sources. In this lecture, we talked about the concepts of reflection, refraction, and transmission. We talked about dispersion and the separation of the colors due to the different frequency of different wavelengths. We talked about inverse square law and how that affects exposure with single point light sources. And the last thing we discussed was the concept of polarization and how we could use that in our photography to increase the richness and color saturation of our images, and to look at other effects like how we can get more transmitted or more translucent or clearer type of water up here in the beautiful tropic area of North Queensland. We also talked about the difference between linear and circular polarization filters, and we discussed the concept that we need circular polarizing filters for our modern digital SLR cameras. So that pretty much wraps it up, our lecture on science of light. I know it's kind of scary in some parts. It is very technical and scientific. I've tried to break it down into a more comprehensive or a more simple way to understand it. As educated photographers, these concepts are really the basis of understanding the technical areas of photography. Don't be afraid of it. If you're a little bit confused at the moment, just keep studying and it will become a lot clearer. They are just frameworks of ideas and ways of describing how light, which is one of the critical components of photography, obviously, and how it behaves and how we can articulate and describe what it is. So don't be too afraid of it. This shouldn't intrude on your creativity. Creativity is, also one of the critical things of photography, but it's just a way of, if you know how things work, you can then bend the rules and actually apply different techniques to get the effect that you want. So that's pretty much a wrap for me. So thanks for listening, and I'll hope to talk with you soon. Bye-bye.